Good evening, everyone. It's with great pleasure that I welcome you all to this insightful webinar organized by the Astronomy Club of the University of Sri Jayewardenepura. Today, we are about to explore how a strong foundation in physics can be transformed into tangible impact through biomedical engineering. This session, From Physics to Impact, Engineering Biosensors and Your Career, is not just about technology. It's about vision, perseverance, and the powerful intersection of science and society. Whether you are a student, researcher, or simply curious about interdisciplinary science, today's session promises to expand your horizon on how innovations in biosensing technology are changing lives and careers. And moving on, don't forget to follow us on social media to stay updated on our latest events. We have already shared the links in the chat box. Make sure to check them and stay connected with us. Okay, so moving on. Okay, great. So today we are truly honored to have with us Dr. Isuru Karunaratne, an inspiring scientist whose journey from material science to biomedical innovation exemplifies the limitless potential of cross disciplinary knowledge. Dr. Karunaratne is a bioengineering scientist at Novoheart, where he develops cutting edge biomedical solutions at the intersection of disciplines. His work focuses on biosensors, biomens, and the mechanical characterization of biological tissues, all aimed at enhancing the way we understand and monitor human health. His academic journey began with a BSc in Material Science and Engineering from the University of Moratuwa, Sri Lanka, where his early interest in sensor design and biomedical instrumentation took root. He went on to pursue a PhD in mechanical engineering at the Hong Kong University of Science and Technology, specializing in biomeds. There, he developed a wireless contact lens sensor capable of assessing ocular tissue deformation, offering a non invasive method to study the eye's biomechanics. Dr. Karunaratne's postdoctoral research introduced a novel technique to improve intraocular pressure measurements, a vital advancement in the early detection and monitoring of glaucoma. His work has not only been published in leading scientific journals but also recognized internationally, earning him a US patent and multiple invitations to speak at global scientific events. What sets Dr. Karunaratne apart is not just his research, but his passion for translating core scientific principles into real world healthcare innovations. Today, we'll hear from him not only about biosense technology, but also transitions of interdisciplinary learning and how to build a path that merges science with purpose. Okay, so now, without further ado, let us warmly welcome Dr. Isuru Karunaratne to lead us through this exciting session. Sir, this virtual stage is yours.
Can you hear me?
Yes, sir, we can hear
Oh,
you.
great. Okay, thank you, Sanogi. It's a generous introduction. And I should first thank Professor Lilani. Well, our meeting was a bit, I would say, a coincidence, but it was a nice one. And then, well, thank you for inviting me to this great. I mean, I find it quite amazing to speak to you guys. Like, it's a bit different from my usual audience, I would say. So today, I guess it's a bit diverse one, which I would like to identify a bit before the talk. Let me share my screen first. see something?
Yes, sir, we can see it.
Okay, give me another moment. Just to understand the audience, can you, I mean, I'm not sure how this will work. I mean, how fine this will work, but can you show of hands, like how many of you guys are from physics? Just, I think you have a hands up function. Yep. Uh, Professor, yeah, I know. How about the others? Because it'll help me to um, understand the audience a bit, like whether it's from engineering, whether we have someone from medicine, hopefully. Okay. I only see like two. Okay, anyone from engineering? All right. I don't think it's very effective that way. Anyway, so I'll start. Um, I mean, Sunny was accurate. Like, today's talk is actually about interdisciplinary research, like applied research, because I'm from an engineering background. And as you saw, that I was initially from a material science and engineering background. So it's quite close to physics of all other engineering disciplines, to be honest. Um, Physics and also chemistry. So I think I will have a grasp of things than people from other engineering backgrounds. I'll start. First of all, I will need to go through a bit of, I would say, biology in terms of uh, paving the path to understand the whole research I'm going to talk about. I plan to talk about one of the researches which I have come a long way from, like the initial brainstorming up to final applied research. So I will walk you through that. So bear with me for the initial background, which you will definitely benefit as not for a physics point of view, but in general. I first talk about. Let me see. All right, I think you can see my first slide or second slide. I'm going to talk about glaucoma. Glaucoma is as you can see some points. I'm not going to repeat everything. It's an irreversible vision loss, yes, and it's the second leading cause. But I guess you might already know the first leading cause for blindness, which is cataracts. I think it's quite familiar for us from Sri Lanka. We have a lot of people who, at least we know a couple of people who are in our lives that had a cataract removed surgically. So, having said that, it can be removed. The vision loss can be fixed. But in this case of glaucoma, you can't actually remove it. You can't fix it. Whatever you're left with after you find that you have glaucoma, you will have to live with that until you die. If it is you can see this, you can refer to these two pictures. Let me try to find a laser pointer. Right, I think you can see a laser pointer here. You can refer to these two images here. You can see one is named as normal vision. The text is a bit small. This is normal vision on the left, and then on the right, it's kind of a tunnel vision, like on the periphery. You have lost your vision. But the bad thing about it is that if you have glaucoma in one of the eyes, you will not notice that you have lost your vision because your brain will, account for that with the other eye, and you will not notice that you have already lost some part of your vision. So that's the bad thing about this. And then once you have lost it, again, I'm repeating this, you're not going to get it back. You can just do some not even procedures, some procedures and some drugs, like every day, to keep the glaucoma from progressing, to stop the progression. That's the that's how bad this thing is. Um, I have to get a little bit uh, through the biology of. I think we are all familiar with this part actually. To be honest, from I don't know, grade 9 or grade 10 science. So we have some idea of the anatomy of the eye. I'm not going to go into details. Like, you can just Google or something when you have time. But I will only discuss the specifics which I would need to discuss here. So in this disease pathology, the nerve head, we have the all the nerves in the retina is collected into an optic nerve behind the eye, as you can see in this image, and then it's carried to the brain. If you have any doctors, I could ask the questions, but I am not the person to describe further. So in this issue, what happens is that the retina at the head of the optic nerve gets damaged. We call it cupping of the optic nerve head. The cause for glaucoma is not, even up to today, it's not known. We don't know why it happens. So we just know it happens. We don't know why. And then, but the medical science have already found that it can be controlled, and it is driven by the intraocular pressure, which is the pressure of the inside the eye. I'll go a little bit deep in that topic. So what is IOP, intraocular pressure? So first of all, we you might have heard, like, I mean, pressure in the eye in other languages as well. Like, first of all, why do we need a pressure in the eye? The answer to that is that we have some optical elements in the eye, as you know, right? We have a lens. You can see I have a small cross section of the eye, of a side of the eye. So we have the lens, and we have the cornea, the transparent tissue at the, I mean, the outermost layer of the eye, and then we have some fluid inside, and this has a power as a lens, right? So we have an optical setup, and it has to be kept in shape, and that's why we need some pressure inside the eye. We have to keep the eyeball inflated, otherwise the brain can't focus on things. That's why we have an intraocular pressure. I call it IOP from now on. So how it's maintained is that, so in this section, you can see uh, this is the anterior chamber, the front side. I can say just in front of the lens, the anterior chamber of the lens, and this is the posterior. It's the posterior chamber is actually filled with a jelly-like semi-solid body, and the anterior chamber is filled with very thin, like watery kind of liquid, which we call aqueous humor. And this is produced from some glands over here, and then it's flowing into this anterior chamber and going out of the eye. It's a dynamic system. It's being produced and then being drained. This drain has a little bit of restriction, like resistance for this flow, and that's how the pressure is maintained. So you know that pressure, I mean, we have many units that we measure pressure, right? But as long as biological fluids are concerned, one of the fluids which is very familiar to you should be the blood pressure, right? So blood pressure, I think systolic and diastolic, it's 120 and 80 should be the numbers for normal healthy people, but it depends on many factors. But I'm just saying. So in the same unit, millimeters mercury, we measure the intraocular pressure. For normal adults, we have found that it's around like 11 to 21. So within that range is normal. If it is higher than that, well, it's a problem. It's very less cases that it's lower than that, and it's a problem as well. So so now you have a kind of an idea why, what the functionality of this IOP, and then the build of the eye. And uh, glaucoma has been found to progress with higher IOP, intraocular pressure. So again, this is not the cause for glaucoma. It's feature of glaucoma, I would say. There are many different types of glaucoma, and then some types it does not. Well, I'll mention some names. One is normal tension glaucoma. It's a less common kind but as the name implies, it's normal tension. That means in that type of glaucoma, the pressure does not increase. The IOP is in normal range, like 15. I've measured my IOP. It was around like 11 to 12. Still, even in that kind of a pressure, glaucoma can be there as a different kind. So the most common kind is we call it POHE. Uh, let's not go into detail, but in that one, that's the most common one with high IOP. It will have like more than 21, 24, even 30, even more than that with like worst cases. So although it's not always evident that the IOP is high in glaucoma patients, doctors have to use some kind of method to screen people who has glaucoma, right? So not really diagnosis, but the doctors use measuring IOP, the IOP measurements to screen glaucoma. Uh, on your right, you can see some images over here. I'm not sure how many of you have been tested using one of these. Maybe this one, the rightmost one, is a bit familiar to you. Like you keep your chin, like rest your chin on that, and then you get an air puff on your eye, and then it gives the reading how much of it's a kind of an applanation. It's going an air puff and figures out how much of an area in the eye gets flattened. So that's how they figure out. I mean, it's all physics actually. It's just giving a momentum of air, and then it flattens an area of the eye, and then how much of an area refers to the pressure. It's simply force divided by area. So that's that's the method they use for screening glaucoma. I mean, it's not complete, but the thing is that this measurement is quite quick. It's like within matter of like a minute or two, they can measure your eye pressure. So if it is on the high side, they will definitely go into the other steps, which are retinal examinations and visual field tests. Both of these things can confirm that you have glaucoma. That means like they will ask you to look at a center point and then check whether you can see things on the periphery. Basically, basically make an optical map where you will give a response to the doctor. Okay, I see that point. I see that point, like that. So in your visual field, that's the best. I mean, that's the method they use to check whether you have any vision loss. If you have any vision loss, then they will try to find what the cause of that is. So that's one thing. And the retinal examination they do, I think that's they're checking the the optic nerve head cupping. I showed you one image in the first the second page. There was some irregularity on the optic nerve head. It's like a hollowed out kind of structure. They're checking that from by dilating your pupil. Um, those tests actually assess the damage, not it's not prognosis. It's not they can't check whether you are in the path to catch glaucoma, not catch like you basically glaucoma development cannot be um, checked before you get glaucoma. That's the main problem. That's what we are trying to solve actually. So again, high IOP is an indicator used for screening, but it's not always the case. Another problem of IOP is a function of time. For example, like in the morning, if you test IOP, the IOP is low. And then at night, when you sleep, the IOP is high. But the doctor is checking your IOP during office hours. It could be 18, but at night, who knows? Your IOP might go up to 25, which is not good. So to test that, uh, doctors have they have one method, one promising method, like it's accurate method. to do a sleep in lab kind of procedure. They basically get you to sleep in one of the labs, and then every 2 hours, they just wake you up and then use one of these tonometers. We call these tonometers to measure your IOP, and they make profiles of IOP like this. You can see in this graph. Um, well, it's not an easy process. It's not a cheap process because you have to be attended by a doctor, a qualified professional, to measure the IOP for 24 hours. And it has to is not convenient. Of course, not convenient because you have to sleep in a different setup, and the IOP has to be measured. So this brings us to the problem statement of the research I'm about to share with you. Okay. Um, so with the story, you should now understand, like, if you have a method to measure the IOP continuously, like let's say we make some, you know that these continuous glucose meters, like continuous like EEG machines, and this kind of continuous measurement, if you have something to just wear it and then just spend the 24 hours at home, and then you get a nice profile of your IOP, and then you give it to the doctor when you meet him next day, and the doctor will give the diagnosis. Oh, at night it goes up to this much. Oh, it's not good, we should treat you, like that. So that's the motivation for this research. So with that motivation, not it was not only our group who did this research, actually. So we had competitors, we still have competitors. Well, I'm now out of this research, but the competition is still ongoing. So by the time I was doing the this research, the state of the art was the Sensiment triggerfish. Sensiment, I think it's a Swiss company. They had built a contact lens which is wearable, basically. Yeah, of course, wearable. And then you just where you can see in this image to the right, the lady is wearing a patch kind of antenna, like on her eye, and she's smiling. I think she was asked to smile, so she's smiling, and then she's wearing this unit on her, I don't know, on her waist maybe, and then wearing this for 24 hours to get the measurement. So this profile is an example profile they get from this measurement. All right, so they have um, their technology is quite simple, actually. It's a strain gauge, which is I will try to ask some questions from you guys. I don't get any feedback, which is not good. Because I want to know whether I'm talking a language, whether I'm speaking a language which you guys understand. So this sensor technology is a resistive strain gauge kind of technology. They have two strain gauges which are radially placed, and then when the theory behind this is that when the pressure in the eye changes, the shape of the eyeball changes. So because it's simple, right? It's like you inflating a balloon. Like when you push more air, like the pressure increases and the size increases. That means the radius increases, the curvature decreases, right? So they're basically utilizing two strain gauges to measure this deformation. That's the idea. Well, that's the theory behind any contact lens sensor which is applied for this purpose. The technology could be different, but the theory is same. Like, it's whatever you wear it, it should be a deformation sensor. So we are slowly now coming into the physics of this one, well, physics or engineering of this one, because the biology part is now, I think, almost over. So I need to discuss a little bit about wireless sensors, LC sensors. Now I need some input from someone. Do you Are you guys familiar? Are you guys familiar with this technology, the LC resonators? Like LC resonators. Have you guys heard of it? I mean, anyone? Someone, please. No one is going to answer me. I'm sad. I just want to know whether physics graduates are studying electromagnetics, also just a simple LC kind of parallel and serial LC resonator circuits. Are you guys familiar with that? Physics guys.
Typical Sri Lankan students are quiet. So
Come on, yeah, exactly. I need some input here. Like I I have all the cameras like closed and then I don't hear anyone speaking. It should be a, like it's not a I'm not doing lecture. I'm not doing lecture. I just want to do a discussion.
yeah,
Although
guys, you
I
can
could name some
answer.
people. I see I have the list of participants here.
Yeah, even you can answer through the message. I mean, messages also.
Yeah, I mean, okay, yeah, sure, why not? Um, you guys have a chat, right? Anyone chat, please? Come on, guys. No one. Okay, you guys are like determined. You're not going to talk in any under any circumstances, right? Okay. I mean, Professor, you can help me. Like, do these guys learn LC resonators? I just want to see how deep I should talk about this.
Yeah, they do. You can
Like,
consider that. Yeah. They do these things now, even just 2 years. So they have, simply they do it.
so they
Yeah. They
do simulation kind of equations.
but they do sessions, but yeah, they have those theories to learn. Maybe in research, to
Go
simulate.
for it.
Yeah.
That's good enough. Not
Me.
exactly. I just continue then. Well, I really would at least get some questions ready for the end, guys. Like, it shouldn't be either you understand everything or you understand nothing if I don't get any questions, right? So I don't think it's the case. You should have to challenge some of these theories. Actually, you should be familiar with this more than I am, actually, because I'm an engineer, to be honest, engineer with a PhD, right? So I know some things to a deep kind of level, but in general, I am not very strong in the theories. Like I don't have the basics that you have in the Maxwell theorem, for example. Like I have not studied that. I mean, you have the it's a luxury actually, because for research, the basics, the understanding of the basics is really important. I need to emphasize that like more than once in this presentation. Well, let me continue. The technology I'm using, well, we are using for this contact lens sensor is LC resonators. LC resonator is well, it's the most simple case of a resonator. Is you can see in this diagram I'm showing here. I can show some images in the uh, slides to come, but this is the most understandable version, the schematic diagram. You can see there's an inductor. to come, but this is the most understandable version, the schematic diagram. You can see there's an inductor, and there is some resistance, and then there is a capacitor. If you have a capacitor and an inductor connected simply, like you have two nodes in the inductor, two nodes in the capacitor, just connect these two together. And when you do the connections, you do it with copper wires or some other cables or something, and they have resistance, right? So we usually, when we don't intend to have resistance, but we anyway have it, we call it parasitic resistance, right? So at least from the parasitics, you'll get the resistance. So this RS will anyway be there, even if you don't like it. So there will be a inductor which you wanted it there, and there will be a capacitor which you intended to have it there. So in this kind of circuit, is called an LC resonator circuit. It has a resonance frequency. I would call it a natural frequency as well. Like it has a resonance frequency such that it can resonate if you supply power into this circuit. So this is if you have this inductor, I mean, if you are into electronics, you might know that there are some chip like inductors. I'm not talking about this kind of an inductor in this case. I'm talking about the most simple coil, like basically a coil made with copper wires or something. We have a coil there, and then we have a capacitor. We connect these two, and we have this thing, a coil and a capacitor. So this is what I call an LC resonator. So if you have another inductor, in this case, it's another inductor, and this circuit I have mentioned it as a network analyzer. So since you don't answer me, I don't know whether you have ever seen this instrument. So this is a network analyzer with which we can connect a simple antenna, a wire loop into this instrument, and then give some power into this loop, and you have the LC circuit. When you bring that LC circuit close to this loop we call it an antenna. That's a familiar term to you, I guess. So we call this a loop antenna. We bring this LC resonator near this antenna. These two gets electromagnetically coupled, inductively coupled. So this instrument can measure the natural resonance, the resonance frequency of this LC resonator without connecting it, like basically without hardwiring it. So this technology it's actually quite simple than you think. Like in this case, say that if you have a varying, like a sensing capacitor, let's say we have a special capacitor which changes its capacitance with pressure, for example, or temperature. Let's say temperature. It's not a usual case, but it's easy to understand. Let's say we have a very sensitive capacitor which is sensitive to temperature, and you have an inductor. Okay, so we have this LC circuit in somewhere, I don't know, somewhere near inside your water bottle. Okay, and then inside your water bottle is your sensing capacitance and connected inductor. When you bring your water bottle near this instrument, it will say that the natural frequency, the resonance frequency of your bottle, I would say, of your bottle is this much. And when you put some hot water into that and bring it closer to this one, the resonance frequency changes from the initial value. In this case, let's say you put water at 0 degrees, bring it to the device, you measure the resonance frequency, you put like boiling water and then measure again. You have 2 points, and then you do calibration. You call that calibration. So if you do that calibration, and after that, whenever you have some water, you bring the thing to this instrument and measure the resonance frequency, you simply can measure the temperature of your water bottle. That's the basic idea of any sensor, like literally any sensor. So you have to do some calibration, some sort of a calibration, because the sensing signal is not really the unit that you want. For example, like thermocouples, right? So thermocouples output a very teeny tiny voltage. It's not outputting Celsius, right? So what they do is they have some circuitry to measure the voltage and then calibrate it with simple, maybe simple, just water, like boiling point and freezing point at sea level should be constant, right? At one atm pressure, so it should be constant. So that's how we calibrate sensors. So even in this case, this one is a wireless sensor. Wireless, when you should now understand, being wireless here is not involved like huge amount of circuitry like chips and ICs and resistors, capacitors. No, not that much of circuitry like your Wi-Fi router, which is also wireless, right? You're not your like not like your mobile phone that has wireless carrier like GSM, right? So not that kind of wireless, but this is a very simple uh, wireless technology, and it being simple gives us many advantages, which I will discuss in the next slides to come. Because, for example, like the previous contact lens sensor I showed you as state of the art, the Sensiment triggerfish lens, it has a chip inside, and then it communicates wirelessly, not with this kind of a simple technology, but digital kind of communication. That means like it reads the strain gauges and converts that into digital, and then transfers readings with some other computer. For that, they need to have like a couple of millimeters chip embedded in the contact lens. So chips are not going to be like 2 to 3 microns thick. I think you should have the idea, right? Like it should be at least a millimeter thick, right? I think less than a millimeter, let's say half a millimeter, 500 microns. And then the contact lens has to be even thicker to embed that chip inside such that it doesn't scratch your eye, because the chip is hard. It's very like it's like having a sand particle, like a couple of millimeter sand particle inside your contact lens, embedded in your contact lens, and then you're wearing it. So it's a bit of a concern, right? So making it thin and flexible and not having stiff, hard items inside is kind of an advantage, because when it comes to commercial contact lenses, like you should be familiar with contact lenses, right? So when it comes to commercial contact lenses, it's actually less than 100 microns thick. It's around 30 to 70. I'm pretty sure it's less than 100, the ones I have measured. So it's from a very it's from, they're made from hydrogel materials, and then it's very soft and also very thin. You can you can't actually feel it when it's on your finger. It's that soft. So compared to that, the one you saw in the previous slide is quite thick and stiff to embed the chip. So in this technology, I'm going to progress. Let's see. Sorry about that. So we are going to design a chipless thin contact lens sensor, which can even be thinned if this works. So this is an initial proof of concept. So it has a inductor. You can see the one I was talking about. It has an inductor and it has a capacitor. But this is really thin. This can be made like within 20 to 30 microns. So the whole lens can be around, I think the lenses we made, it's around 100 to 120 microns thick, as I remember it. Well, this is where the physics comes in, and my research, the research I'm going to talk about, is actually based on physics. All up to 3 to 4 years, we have been working on this physics part for this technology, because all the other research, the bio part of the research, is not done by engineers or us. It's done by doctors. When the product is ready to launch, we have to contact like real world doctors and people to get the research going. So that's how it works, right? So most of the time, so we started, I mean, I started from this lens actually. It's not, I didn't start from scratch. So you can see there is one inductor and a capacitor. And the technology is that I already told you that when the pressure changes, the eyeball changes the size. So the inductor changes its diameter, its average diameter, and that changes the inductance of the inductor, which in turn changes the resonance frequency of the LC resonator, and it can be read wirelessly quite easily. But there is a catch. The catch is that when we wear this contact lens in our eyes, it's not in air, right? It's in a liquid environment. Especially, it's a salty environment. It has some ions dissolved in this the tear, right? And the concentration of the salts, I mean, I'm in the concentration of the ions is not constant. You know that we sometimes like don't blink. We just keep our eyes open and the tears dry out and then the concentration increases, right? And then we close our eyes. The I mean, and then we might cry. So the concentration changes obviously. And then with these changes of the concentrations and the compounds in the liquid medium, what changes? The parasitic capacitance changes. Not It's not just parasitic resistance which is there. When you have a coil inductor, you have inductance, of course, and you have parasitic capacitance between the coils. And I tried to show, I mean, do a small diagram of it. Some of the parasitic capacitance are due to electric fields inside the contact lens body, which is okay because it's not changing a lot. But there is one component, at least some components outside the contact lens body. So when the tear concentrations change, when, for example, if you just simply change the sodium chloride concentration of a sodium chloride solution, basically a salt solution, if you change the salt content, salt concentration, the dielectric constant changes, the permittivity changes. And then when the permittivity changes, the resonance frequency of this LC resonator changes. And then this contact lens becomes a permittivity sensor, uh, not a deformation sensor. That's the catch of this kind of sensor. So that's why that should be why the Sensiment triggerfish lens guys using digital technology, yeah, to convert the strain gauges to digital kind of information and then transfer it in a different technology. But it has its drawbacks, right? But we have to deal with our drawbacks. So this is where I started the research, and then what I did was a very simple um, logic actually. So what I did was, instead of one sensor, I tried to embed two sensors in the contact lens. That's what I did. Well, that's that's what I did for 4 years actually. So it's not as easy when you say it. The hope is that both the sensors will be affected by the environment identically, or at least proportionally, like similarly. So the two sensors will be affected similarly with the environment, because the both the sensors are in the contact lens and similar kind of environment. When you cry, the concentration changes similarly. That's the idea, right? So, and the other fact is that it should be differently affecting the eye deformations, get affected by the eye deformations differently. That's the idea. Otherwise, the signals cancel, right? So this is a very simple logic, such that it's this differential kind of sensing technology is not new. It's not reinventing the wheel. Actually, it's very common. So if you have a sensor, if you have something somewhere, and then you try to measure it, and then compared to measuring one, if you can measure two, and one is sensing differently and the other is sensing differently, the differential signal says a lot. If you can design these sensors such that that difference is what you want to measure, it makes a lot of sense, because you can get rid of many other noise from this differential signal, because hopefully the noise is common to both of these sensors. So that's the idea. But that idea was not that simple, because I was not a physics intellectual as you guys are. So I didn't have any idea of electromagnetics, and then I had to learn it from scratch. When you keep two inductors close to each other, then they talk to each other, which is not good. um when the two inductors talk to each other, that's what, because you want them to operate like independently, right? You want this to be affected by the environment in a, like, let's say, in one way, and then the other coil, the environment, effect of the environment, same way. But let's say, for example, for this kind of a setup, like you have a larger coil and a smaller coil, right? So when you have a lens, when you have some deformation, the larger coil will be deformed more and the center coil will be deformed less, right? So there's a definite difference in the deformations. But if the environment is affecting both of these guys similarly, so it's a win. But now, when I keep two inductors like this close to each other, what happens is that they talk to each other, and they don't even give, in some cases, they don't even give me two distinct resonance frequencies, because they couple. I could not solve this for such a long time, and to be honest, this I go back one. You can see I have two designs. In the left, you can see there's one, like, two kidney shaped lenses, sensors, and then the bottom one is, we call it the concentric contact lens. We call this asymmetric contact lens. So this is actually the one which is preferred, because obviously we have a hole at the middle, and then the person can see through that, because this one is like a cat. I don't know. So it's very small, and it blocks the visual field. So obviously this was preferred, and this is where we started it. And then what happened was, I could not solve the coupling. I could not solve the coupling for 2 years, actually. So we struggled a lot with the kidney shaped contact lens, the kidney shaped sensors, but the kidney shaped sensors were too small, and the signal was too weak to be detected by the antenna, and we had a hard time for 4 years, right? And then what I did was, I yeah, the whole group was going in that direction, and then uh, I tried to do an iteration, of series. It's actually a matrix of an array of experiments, with changing the capacitor sizes of these resonators, and then I found a window where I got two separate resonance frequencies, with the two um, resonators being concentric. And then I simulated the same kind of an environment, like the environment, and also the geometries, and I could repeat that. I could benchmark that. I mean, benchmark what I got practically from the simulation model as well. So that changed the things actually, turned everything around, because this setup gave us a very strong signal, and then it could solve the problem. If I just describe what is on these two graphs, is how we solved it is that the frequency of the small coil has to be, well, in this case the frequency of the small resonator is larger than the frequency of the large resonator. So in that case, you can see the combined dual resonator signal is the green one, and you can see you have a very strong peak. That's one of the resonance frequencies, and the other one is really weak. But when the small coil frequency is smaller than the large coil frequency, I get a nice two peaks. I could read the two resonators. It is coupled. I'm not saying it's like uncoupled, but they are coupled. But still, I have two readings. And with those two readings, you can see here, like F1 and F2 in this one, in this graph, correspond to the two signals. You can see the circles, the triangles, and the squares correspond to three different environments, three different sodium chloride concentrations. You can see 0.85, 1.05, and 0.95. These are the three. Well, not in that order. I don't have the legend over here, but you can see for this kind of a salt concentration difference, you can see how big of a level shift of this the characteristic curve goes. Like for example, F2, it changes around 1 megahertz for this change in salt concentration, right? And even this one similar, a bit less than I think it's the same scale. The change is a bit less than 1 megahertz, but you can see the IOP, the pressure measurement, I'm changing the pressure from 5 mmHg to 45 mmHg. It's covering the human like physiological range, but you can see the change I get. The actual signal I want to read is actually around 0.3 megahertz, where the difference from the salt concentration is close to 1 megahertz. So my signal is doomed. So with the differential signal, when I subtracted F2 from F1 with it was with a linear factor. With the linear transformation, I could embed F2 and F1 into a differential signal. You can see it was nicely coincided. You can see for all salt concentrations, I could get a nice single curve. All these curves are coincided, and then I get the differential signal. So you can see I converted this megahertz into mmHg in the next graph. Set IOP is I am controlling the IOP of this signal is from a model I, and then when I set the IOP from 5 to 45, you can see from the reading I get 5 to 45. The dashed line is actually the ideal curve, and then you can see the signals I get. The error is within plus or minus 3 mmHg, which is comparable to the error we get from commercial tonometers. So that's a win. So then the technology is ready, and the sensor we had to work a lot to make the lenses, because we are a university, right? Like we don't have commercial technologies to make contact lenses. We built everything from scratch. Like we built molds and like molding methods for contact lenses, and we finally succeeded. We got contact lenses which do not harm the eye. So from the simulation and quick and dirty experiments, we went into synthetic models. That's where you saw the salt concentration experiments and everything that was on these synthetic models. And then what we did was we went into like in vitro biological experiments. So this is a bit disgusting, and this it's a porcine eye, it's a pig's eye. Since you don't speak anyway, I don't hear the disgust, so I don't mind. This is a pig's eye. You can see it's pierced with a needle, and then it's the needle is going to the anterior chamber. So it's anyway a very watery kind of fluid in the anterior chamber, if you remember what I said. So we can simply use a saline solution to increase the pressure of the anterior chamber, basically the eye, and then change the diameter in the physiological ranges of the pressure, right? And then we can measure the signal from this setup. So that's in vitro. We call it in vitro, like outside the body. And then, yeah, it's not very ethic. That's the real world. We have to then test with animal. Luckily, I didn't have to kill any of the animal subjects. With animals, what we did was that to test the safety, basically. Like we got the rabbits to wear the contact lenses for prolonged times. The doctors did that. That is essential before translating the research into clinical trials. Before wearing in any kind of human, we have to go through the animal trials. So we tested on rabbits, New Zealand rabbits, and then it tested okay. So it did not scratch the rabbit's cornea and did not do any damage. And then we continued into clinical research. This is a very primitive kind of setup. This is a he's a doctor actually. He's one of the eye doctors we worked with in hospital. So he's wearing the most initial setup we did with the patch antenna and then the reader, the VNA network analyzer, and then he's wearing the whole thing in his body, including the computer. So that's how the measurement was recorded. I should point out that during this research, like there's a huge team working on it. I myself had to do whatever the thing I came across, and regardless it being electronics engineering, electrical engineering, computer science, and you name it, whatever you come across, you have to learn, you have to study, and then not the whole thing. If you try to learn it from like A to Z, it's not going to work. Like you have to manage the time and then basically study what you want to study, actually what you need to study, and then continue with your research. But at the same time, like this kind of applied research involve a lot of professionals. Like for example, it needs materials engineers to decide what kind of materials you use for contact lenses. Simply put, the contact lens we used, that we fabricated, was using a material called PDMS, which is a very common material used in microfluidics, like bio kind of research. And then we know that the PDMS material is quite good in oxygen permeability, which is very important in terms of the eye, because the eye is breathing through the cornea actually. Through the cornea, yeah, that's how it happens. It has to be wet and it has to be permeable for oxygen. So PDMS, the material we used, is very good with permeability for oxygen, but the problem was it's not wettable. It's not hydrophilic. The material, the intrinsic property of this material is hydrophobic. We had to turn that around. Like we had to do some treatments, like uh, plasma treatments, and then some addition of new changing surface properties of this material to make it hydrophilic. So this kind of thing, it's a materials engineers kind of thing. So had to do the magic to make the sensor, the contact lens wearable, and also the sense elements itself, like the sense element, we could bring it down to less than 30 microns, 30 micrometers. And also, but at the same time, like the sense elements were copper, like the material was copper, because it's not because we wanted it to be copper. It's just because we didn't have other technologies to make other kind of flexible. Yeah, I mean, if we have like chemical and materials guys, like polymer guys, for example, here, they should know that we have like conductive polymers, we have conductive other kind of coatings, kind of thing, which are flexible compared to copper. It could be better, but with the technology we had to go with copper, and to make it biocompatible, which is not, copper is not biocompatible at all, so we had to encapsulate it in gold, and also some parylene coating. We call it parylene C coating. It's a nano level coating which we have a separate like physical vapor deposition PVD kind of technology to apply the coating on the lens, such that the proper elements are not like exposed to the biological environments. So we had to encapsulate them very well, because we are dealing with patients. We are not joking. So since we know it, we were the first ones to wear the lens and check. To be honest, like even before rabbits, we trusted the lens and we wear it on our own. It's our it's a risk. It's a risk actually. So it's just the trust. So material science and physics, you're obviously the things I discussed up to now, it's mostly physics, so obviously we need physics to design this one. And then electronics engineers are needed for creating this wireless readout circuit, which I'm not good at. I'm capable of creating a simple like Arduino kind of circuit and then maybe some PCBs, but I'm not good at wireless technologies for electronics, for example, like communication, kind of communication. And then we needed electronics engineers for that. And then we had to get the service of well, we wrote some programs on by ourselves for some live reading using MATLAB, using C++. And then but when it came to machine learning, for well, we did machine learning to a certain level. Again, we had to learn that. So but we still needed computer science guys to continue with the you know the commercial kind of level in machine learning. So and then when the technology is ready, like for clinical research, we obviously needed ophthalmologists who eye surgeons, eye doctors, to work on the clinical trials and data collection. So it's a huge team, and many in many disciplines. So it's very important to have these like different approaches and different ideas from different kind of professionals in this kind of applied research. So this was completed in well, it was just before COVID. It was ready for clinical trials, and then COVID hit, and we could not continue the clinical trials for so long. And then after COVID, we restarted the clinical trials, and then we could start publishing. Well, I graduated with, I mean, this is my PhD research. So I graduated in 2021 June, and then you can see these publications are even after that. So they're still working on it. You can see publications coming in 2025 here. So now the doctors have confirmed that the contact lens is tolerable and safe to wear in humans. Like they have done some study involving 30 adults, and then they continued. So 59 adults, they showed that some they like they distinct they show a distinct difference between like subjects aged less than 30 and um, over 30. So they saw difference between these kind of different classes of subjects. And then some in some other experiments you can see uh, from a sitting kind of position to like a sleeping, a supine kind of position change can change the IOP. Actually, that's a known fact. It's I think it's because of um, the vascular pressure, like the blood pressure actually. So that causes the IOP to change as well. So in this study, the third one, they confirmed that the CLS measurement, the contact lens sensor measurement, they did agree with the tonometer measurements for changes from sitting position to supine position. So all these studies confirm that these are compatible. Like the readings are compatible with the commercial tonometers, and then oh, well, they're compatible with the readings, but at the same time, the see a 50 hertz trend in your sensor signal. Like that's from the sine wave of the power signal. Like I've seen that myself actually. So I'm not the best guy to answer that, but still, like they have to be dealt with first thing with analog electronics, and then after you obtain the signal in digital signal DSP, digital signal processing. So if you're doing mechatronics, I can't really like specifically say, oh, okay, you should learn these skills specifically, but it will definitely help if you study electronics in the analog domain. But the sensing principles, I don't think it can be simply described as, oh, you should just learn this part. It's it depends on the project. It can vary from some uh, if you know it can be simply I mean measuring resistance to kind of a surface plasmon resonance kind of measurement method. So it's a huge range, but a general knowledge will definitely help you. Mechatronics is quite interesting field, and then because you have the touch of mechanics and also the electronics part, but um, learning some of the electronics side will definitely help you if you want to go towards the biosensing side. Did I answer your question, or did
Thank
I
you, sir.
walk around?
Yeah, 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 good answer.
Yeah,
And I have another question.
yeah, sure.
Acknowledging limitations that can sometimes challenge practical learning opportunities in countries like Sri Lanka. So, what avenues would you recommend for students to gain meaningful international volunteering or internship experience in this kind of field? Are there
Can
any
you
specific programs or institutions or proactive engagement strategies you will recommend?
can you repeat your question? Like starting
In
point.
Sri
Like
Lanka, there are so many resource limitations.
yeah.
So, what avenues would you recommend for students to gain meaningful
Got it. Got
international
it.
volunteering
Okay.
or
For me, I'll tell you just did yeah, Professor did tell me that just mention how I came across this well how I came up here. Okay, so I started as a materials engineer. I never wanted to come into academia, and then I I was not on in like top of my class or anything. I'm just a mediocre like engineer, right? So I didn't. I just had a second upper, and then I started. Obviously, I didn't even. So some of of our friends like they stayed in the university to do. I mean, being RAs and trying to go for scholarships and everything, and then I had no idea about that. I mean, I didn't want to do that. I just went straight ahead to do a job. I was a good engineer. Trust me. I'm not very strong in academia, but I think I'm good at engineering. And then after 2 years doing engineering in Sri Lanka, then I was fed up. Like then I had to do the same thing again and again, and then uh, that made me think I should do something else. My brother was also doing a PhD, and well, he was playing cricket and then everything. And then I wanted that as well. So that's what made me do a PhD. That's why I stopped what I was doing. I had a decent job compared to what I mean above average job compared to what my friends had. So, but still, I dropped it, and then well, yeah, of course, I secured my position before I dropped my job. But what I did, I want to tell you that I simply did start applying for. I selected some universities, um, NUS, NUS means National University of Singapore, and then HKUST, which I did my PhD. Those are the two institutions I have ever applied for. And then what I did was I selected some specific professors I wanted to study. Basically, I went into their biographies, like in the campus, the university websites. You have, I mean, they have their profiles, right? So we can understand what their research is about. So I selected, like, I don't know, 10 or 20 um, people who um, I was interested in. Then what I did was I emailed them. I emailed them saying that I'm interested in your research. If there's any opportunity, um, I would like to study. I mean, I would like to have an opportunity to study under you. I mean, in your group. So then I accepted my first response. That's what I did. It was in HKUST, and that's how I got it. I, as I told you, I didn't have a first class. I had like one or two papers which are very, very bad, and still, I made it through. So similarly, what you could do is that don't limit yourself. If you're doing physics, if you're doing mechatronics, if you're doing whatever the thing, don't limit yourself to that specific thing. There can be many other opportunities in the world which you even don't know that you're qualified to do, right? So try to open up yourself, like read the I mean, you can just simply go on chat gpt, and then it's even easier than Google search, right? So uh try to understand what your capabilities and your passions can achieve, and then try just try applying. That's what worked for me, right? Don't like procrastinate. Just go on email and just put an email, like attach your CV and get your transcript and just send it out. And this is similar for internships, for exchange programs, for whatever you name it. Just do it, right? Get your CVs right. Don't have like spelling mistakes, grammar mistakes in your CVs. You have more than, I mean, if you have a mistake in your CV, that says something about you. It doesn't say anything about your English. It says about your negligence, right? So it doesn't look good. So your cover letters, your CVs, get them right, and then just do the application. You might need to do some IELTS exam or some other qualification examinations, which some universities require, and you will definitely get some answers. So you might need to be a bit flexible on selecting your topic to study. For example, if you're doing an MPhil or a PhD, you might need to be flexible a bit on your side, because it's not the case that you will be allowed to continue your idea of research in all the cases, because the funding is a bit funny. Because for bio kind of research, it can have funding, while pure physics kind of research might have some difficulty in obtaining funding, right? So if you talk to a professor and say, hey, I want to do a nano coating kind of research, and then he might not get funding for that. Like, he might recruit you and then end up having not funding. Is not good for him, right? So he has to maintain you, so it's a burden. So um, you might need to clarify that, the topics and everything before you get into the studies. But at the same time, you're in Sri Lanka, you're studying, and you email is not a paid service. You can do uh, just connect with people all over the world. Just put an email. They might respond. They do respond, actually. they do respond. So you can check like whether you can obtain some quality chances, because there are many universities who have funding for postgraduate research, because they have research to do and researchers to do, and then they don't have the human resources for that. So uh, yeah, that's how you do it. Just basically connect with people, contact people, and then say it out. You don't need to think, oh, I need to learn this and that before before doing this, otherwise they will think less of me and like that. Just say it out, put it out, select some universities, select some people, and then just contact them. That's how you do it. I guess I think there was another question in the list. Did I miss that? Oh, I have that. S- it's from well, first of all, did I answer the question, Sri Lanka?
Yes, sir. Thank
All
you.
right. Okay. There's another question from Angelica. Can you explain how difficult it was to move from BSc in material science to this research field, and what kind of challenges you faced? The main challenge I, uh, well, as I told you, I was a bit capable as an engineer, and then I was I had a hobby in electronics. I never learned, I mean, studied electronics, and then for translating my research to this one, I did definitely use my skills in material science and engineering. Okay, to others, the question is that I mean, was it difficult to transfer from material science to this field, right? So yeah, it was challenging, of course. The challenge, the most challenging part is to uh, that you have to study some things that you never studied, like not even your field. For example, I mean biology. Like I had to be up to date and also competitive in defending my problem statement in my research. For example, like I have to challenge a doctor about a field in medicine. So we have to read, we have to like be updated in the very latest kind of publications. And then basically, if you are doing a research, if you are doing a PhD, you know about it the most, like no one else, not even your thesis supervisor, not even any other person in the field, because you are doing it. You have all the time for yourself to read about it, and you have to be updated about it. And if someone asks you, oh hey, isn't one of the like teams in UC Berkeley doing your research, how are they doing, you should be able to answer that question if you are doing that research, because you should know already that how many teams in the world are doing like what you're doing and what they are doing, to be honest. Like that's a bit challenging, I would say, because I'm not very, I don't like reading books similar to journals, I mean, and papers, but that's something a bit difficult for me. At the same time, yeah, the other challenge was to learn different skills. I had to I spent a long time to study the electromagnetics suite for electromagnetic simulation part. It was challenging. I had to do it because I didn't have any other methods to benchmark what I did in the physical world. I did a quick and dirty method. I told you that I made an array of sensors, and I got the two LC resonators to decouple. But I needed well, I had two options. One is to prepare a mathematical model based on Maxwell equations to describe how my two LC resonators are now not coupled. The other method is to have a simulation software to replicate the environment I'm creating, and then get that to describe or be compatible with what I'm getting in the physical world. I was not able, definitely I was not able for the to do the first one. I was not competitive in that. So I had to go the benchmarking method with the simulation software. So I chose that. And then you can see I went from the brainstorming part to the clinical research, right? So you have to learn, like, jump from rock to rock, like study that part, study this part, and then move on. That's quite the challenging part in the applied research, but you have to bear with that. Yeah. And I think I answered your question, Anjali. I mean, let me know if I did not. Um, there's another hunger. If you conduct research across multiple fields, how can we effectively combine? If we conduct research, if we conduct research across multiple fields, how can we effectively combine different subjects into a single study? Vihanga, can you elaborate your question a bit? If you can just unmute and just tell me what it is.
So if we do any research with chemistry and physics fields, if we conduct with that both fields, how we can effectively combine that subjects to a single research?
Well, it's like this. You're not combining two different fields for a study. You're doing a study, and then you're learning whatever you have to learn for that study. That's how it's combined. That's how the applied research works. It's not like you one day just come, okay, I'm going to do a study combining chemistry and physics, and what shall I do? It's not like that. I mean, I'm not sure whether I'm answering a question, but in the applied research, what you have to come up with first is a problem in the real world and potential solutions for that. And then if I chose for the question I described, like for the contact lens sensor, if I chose the I mean at the very beginning, like if I chose um strain gauges, like resistive strain gauges instead of the LC resonators, what I needed to learn in that path would be very different to what I did, because in that path I will have to go through wireless communication kind of things, which is electronics, and then the sensing method will be rather simple, and then the communication will be challenging, and the things I have to learn will be different, right? And then, but in this one, I had to go through electromagnetics coupling, inductive coupling, and decoupling, and then the models to not to I mean, to avoid the two things interacting with each other. So I have to go and study bit of electromagnetics. So that's what I mean by interdisciplinary research. That means in PhD, I mean, when you after the B, I mean, when you're doing the BSc, you have to learn the different fields according to your curriculum, right? But when it comes to a MPhil, or even better, if it comes to a PhD, it's very narrowed down such that you will be studying a very, very specific area of each field. You won't have time to study the whole. I mean, you can talk like a day about your research, but you won't be covering a majority of any of the fields of your study. It is quite understandable and understood in the fields. Like when you're doing a PhD, you're not going to be an expert in the whole field. You'll be an expert on your study and the related subjects. But the subjects are not selected by you first before deciding on what study you are doing. So you have to select the study first, and then depending on that, it will decide which things you will have to learn. So it's a top down kind of method. So but in a way, if you know, uh, this is not a very good example, but if you have a hammer, like you will see all problems as nails, right? So if you have different tools, like if you have a plier and a hammer and a screwdriver, so you will decide in between a multiple tools what to use for this question, and maybe a combination of these, right? So I'm not I'm basically telling you that if you have those different tools, you will have better answers. So if you know a bit of physics and if you know a bit of chemistry, and you will definitely have a better hold of the problems than someone who just knows chemistry, because you have the basic idea and the grasp of the different fields, and you can come up with an answer which is connecting the two a couple of fields. So it's very important to have the basics in. I mean, if you have some idea of the different fields, it's great. It will make you very strong in the problem solving part. But it's still the study which determines what kind of fields will help you with that specific study. I mean, for example, you may be very good at something else, electrical engineering, for example, which might not help with that study at all. So, yeah, did I get it right, Vihanga?
Yes, sir. Thank you.
Okay, no problem. Thank you. Anything else, guys?
Okay, Dr. Karunaratne. So, yeah.
Okay, so Dr. Karunaratne, so due to time constraint, we will have to stop our Q&A session from here, even though it was really insightful and interesting. So if you guys have any questions, you all can contact us through social media. We have already shared our links, social media links, and you can stay connected with us. And we will be forwarding those questions to our resource person, that is Dr. Karunaratne. So thank you so much, Dr. Karunaratne, for taking time to answer our questions with such depth and clarity. It's been such an absolute privilege to learn from you today. And I would we all would love to capture this insightful moment now, and we will kindly invite all of you to turn on your cameras as we take a group photo to mark this
Oh,
occasion.
wait.
Yeah.
Yeah, good to see
Also,
you.
Dr. Karunaratne, as the actual senior treasurer of this club, I don't know, you had met me, so I'm Dr. Kandiban, so we would like to really thank you for almost spending 2 hours of your time. It was really insightful, because the students also were really interactive and they wanted to ask questions, and they are still keeping on asking questions. So we feel it's a really successful talk as well. We'd like to thank Professor Lilani Atigala also for connecting you with us. So I think after a long time we had a very nice talk from a very engaging person, and it's also very practical, applicable side. So we would really thank your time as well as the Astro Club. We would like to actually have you connected with us, maybe so our kids can actually talk more about their higher studies and how they can apply zones. I think this is a different side, so which we had not seen for a long time. So thank you very much for your expertise. We really enjoyed it. I just missed the first initial talk because of some other seminar works, but at least the last 1.5 hours I was there. It was really nice. So thank you very much again, and I think we'll just move on to the photo shoot up, right? So thank you very much again. Thanks.
Thanks a lot. It was quite a nice session. Like I didn't, I forgot about the clock. So the questions made the day. Actually, I mean, initially people didn't talk. I mean, I really liked some interference, but end of the day, I enjoyed the questions a lot. And if you, yeah, as Sanu told, if you have any questions, just feel free to contact even me on LinkedIn or somewhere, and then push some questions. If I can help you, definitely I wouldn't think twice about it. So yeah, thanks for inviting me again, everyone. Yeah, we can go through the photo exercise.
Can we all take a group photo now then? Can you all switch on your cameras? for a moment. Okay, great. So, as we reach the end of this insightful and inspiring session on engineering biosensors and your career, let us take a moment to reflect on what we have experienced together. So, today's webinar was not just a technical discussion, it was a powerful reminder of how interdisciplinary thinking rooted in physics and engineering can create real impact in human health and well being. So, to our esteemed speaker, Dr. Isuru Karunaratne, thank you for guiding us through your incredible journey and sharing your knowledge with such clarity, depth, and passion. So, your story had inspired many of us to think beyond boundaries and imagine new possibilities for our own paths. And a big thank you to our senior advisor, Professor Lilani Artigala, Senior Treasurer, Dr. S. Kandipan, and Mr. Danushka Dharmasiri, Academic and Inter-University Advisor, for all the hard work and dedication to the Astronomy Club. Your support continues to be the backbone of everything we do at our club. And a warm thank you as well to our executive board, organizing committee, and technical team, and everyone who worked tirelessly behind the scenes to bring this event a success. And of course, to our wonderful audience, thank you for your energy, curiosity, and engagement. It's your presence that makes events like this really meaningful. And as we always say here at the Astronomy Club of our university, stay curious, stay inspired, and keep looking to the stars. Have a great evening ahead. Thank you so much.
Thanks,
Okay,
everyone.
Dr. Isuru.
Thank you.
Thank you, sir.
Recording stopped.